Okay, let's continue. The next section you see is entitled the domain of a function. And we'll define the implied domain of a function to be the set of all x such that the corresponding y is a real number again. At least for a while, we will consider only three situations though. The first, when we're dealing with polynomials, the domain is negative infinity to positive infinity, and that's the interval notation, of course, that we use. This is, again, the representation of all real numbers. Secondly, the fractions. When we look at fractions, they cannot have any number in the domain that makes the denominator 0. And then third, radicals. If the index or root is even, then the radicand, or what's under the square root, or fourth root, sixth root, must be non-negative. Example 5. Find the domain of each of the following functions. Okay, so for part A, we see f of x equals x cubed plus 3x plus 1. Now this is a polynomial. It's a polynomial that happens to have a degree of 3, which, if you recall, we define as a cubic polynomial. It has 3 terms, so we'd call it actually a cubic trinomial. The domain of this particular function, therefore, because it's just a polynomial, would be, I'll write domain, capital D for domain, negative infinity to infinity. The notation that we will primarily be using in this class will be interval notation. You will see some other notation though when it comes to writing domain. And as I noted before, you could also say all reals or all real numbers. This is another good, quick and easy way to identify that particular domain. So, part B, f of x equals 2 all over x plus 2. This particular function happens to have a denominator that we can identify with, particularly where we go back to the second of 3 situations from above. With fractions, we cannot have any number in the domain that makes the denominator 0. So if we were to say x plus 2 can't equal 0, solving for x, then subtract 2, so x cannot equal negative 2. So when we write our domain for this particular function, we identify it as domain negative infinity to negative 2. And then we say in union with, which is just a fancy way to say or, connecting the two intervals. So negative infinity to negative 2 or negative 2 to infinity. Now, we did use a parentheses, just like we did up above, as opposed to brackets. You'll never use a bracket on infinity, whether it's negative or positive. But we did use parentheses on the negative 2 here because, again, x can't be that number. So in a number less than negative 2, not equal to, or in a number greater than negative 2. Part C. F of x equals the fourth root of 5 minus x. I'll highlight my radicand, and my index, particularly, we'll note here as even. Okay, now because the index is even, I'll go back up top here to the third situation with radicals. If the index is even, then the radicand must be non-negative. So we'll go ahead and we'll say 5 minus x must be greater than or equal to 0. So whatever x is, okay, when you plug it in, do 5 minus that number, it must always be positive, and this is how you write a positive number, greater than or equal to 0. So it can be equal to 0 technically. So when we solve this, go ahead and get x by itself. Now I could subtract 5, or I could add x. I'm going to show you this is adding x to the other side, so I don't have to divide by a negative and then flip the inequality, if you recall. Which leads to then, if I just kind of rewrite it a bit, x less than or equal to 5. So my domain looks something like this. We have negative infinity to 5, but now with a bracket. The reason we use a bracket, of course, is because our x values can, in fact, equal 5. Next section, applications. Example 6. A baseball is hit at a point 3 feet above the ground at a velocity of 100 feet per second and an angle of 45 degrees. The path of the baseball is given by the function f of x equals negative 0.0032 x squared plus x plus 3. So just a quadratic equation, which, by the way, because this is a negative, hopefully you recall this, well, in the first place will be a parabola, but because it's negative, it's going to be a parabola that opens down, as you kind of see here. Where x and y are measured in feet. Will the baseball clear a 6-foot fence located 200 feet away? So what we're going to go ahead and do here is we're going to take our function, but highlight it as f of, in this case, the quantity they've provided, 200. That's my x that I'm establishing here. And then in turn what my y will be for that x. So if I go ahead and substitute 200 in for x, as you see, we'll go ahead and do the math. Now, if we're doing the math on our calculator, what I do advise you to do is to use parentheses, and you can actually type in this entire quantity as such, and when you do this, you'll end up with a very nice answer here of 75. So keep in mind, I'll go ahead and put the f of 200 out in front again. Keep in mind what we've essentially just come up with is an ordered pair of 200, comma 75. So when x is equal to 200, we now know that 75 is the answer. In other words, 200 feet as an x and 75 feet as a y. So it will easily clear, considering that starting at the 3 feet, a velocity of 100, 45 degrees angle. We really didn't even incorporate that, but the path, will it actually clear the 6-foot fence? Well, yes, of course. Yes. It clears. Okay. Some of the parameters on a word problem we don't actually account for. On that problem, it was as easy as plugging in the x equal to 200. We will now work with an expression from calculus, and it's called the difference quotient. Now, we did discuss the difference quotient in our pretest a bit. Probably one of the most interesting concepts in the very beginning of pre-calculus. It is a very neat precursor to something called the derivative. So when we look at the difference quotient, typically we do look at something as simplified as this. I say simplified, it does look more complicated than some of the things we've seen thus far, but it's simplified in that it's got a binomial, it's got just simply f of, in this case, x, and then all over h. So it is a difference quotient for a reason. It is a quotient, of course, of two things, but it's also a difference in the numerator of those two quantities. So if f of x equals this, x squared plus x minus 1, just a quadratic trinomial, 3 terms, degree of 2, we find the difference quotient. We do start with each respective piece, the first being f of x plus h, so we'll do that first. When we do that, we can say here that x plus h, when we substitute it in, of course, put it in parentheses, and then plus, again, x plus h in parentheses, and then minus 1. So I'm substituting in x plus h here, and then there. F of x, I'm going to rewrite it, just for the sake of getting them both kind of laid out. So when I actually do the difference quotient, I perform the operations. We'll take this entire quantity, I'll rewrite it, and I'll save myself a step by setting up for the foiling of x plus h and x plus h. And then I'll drop the parentheses because we really don't need them any longer, which you'll see very clearly in the next step. And then I'm going to write minus, and I'm going to put this in a kind of bracket here to differentiate. So x squared plus x minus 1. That is the f of x in its entirety, all over h. So this is the difference quotient set up. I'll go ahead and FOIL. So when I FOIL, I'll have x squared first, outside xh, inside xh, last h squared, still x plus h, and then minus 1. And then the bracket is just a helpful trick to differentiate, but also to remind you that you do need to distribute. So I'll distribute the negative, and that's all over h. Still pretty daunting looking, but things are really going to start to unfold nicely. And here's how. You have like terms. X squared minus x squared. X minus x. 1 minus 1. Those terms obviously cancel. Well, these two are going to add up. And if I look through, it looks like that's pretty much it as far as that step goes. So we'll do the math in which if we add xh to itself, we get 2xh. We still have the h squared, and we still have the plus h, all over h. One of the things that you should always be mindful of on any given algebra problem, whether it's complicated or not, is try to see if you've got any common factors. I do have a GCF, particularly in the numerator, being h. And that's the smart variable really to factor out. I say smart, we don't have any other GCFs, but if we did, we would only factor out the h because the denominator only has an h. I'll show you kind of, in that respect, why that's important. You can kind of see that unfold if you see the quantity kind of separated too. You're going to have the h's cancel. So that's kind of a nice preview, so to speak, of other problems. And of course, this guy is going to simplify as 2x plus h plus 1. That's just factoring out the h. We've already divided out the h. So lo and behold, we're left with 2x plus h plus 1. This is actually called the first derivative, which you'll talk with your calculus teachers next year more about. But in this particular instance, we'll keep it simple, just call it the difference quotient.